Welcome, dear students. So we were discussing about normed spaces and its definition. Okay, and we have also discussed about metric induced by the norm. Okay, these are the things which we have discussed. Usually, the metric is defined by p of x y is equal to norm of x minus y. Okay. So now we go get onto elementary properties of the norm. Okay. So the first property or the first result is norm of modulus of norm y minus norm x is less than or equal to norm of y minus x. It is somewhat similar to the result modulus of mod a minus mod b is less than or equal to modulus of a minus b. Here, x and y are element of the normed space x comma y element of the normed space x. So we have to prove that modulus of norm y minus norm x is less than or equal to norm y minus x. So we have a definition which is modulus of a minus b less than c implies minus c less than a minus b less than c. So in order to prove that modulus of norm y minus norm x is less than this quantity, let it be c. We only have to prove that norm y minus norm x is less than this quantity, that is this inequality, and minus of this quantity is less than or equal to norm y minus norm x, that is the this inequality. So we will be proving both of these inequalities. So first we will take norm y. Okay, so norm y can be written as norm y minus x plus x. We just added and subtracted x. Since x and y are elements of the normed space, we can use triangle inequality. So this should be less than or equal to norm y minus x plus norm x. Okay, so moving this norm x onto the left hand side, so we get norm y minus norm x is less than or equal to norm y minus x. So this should be the first part. If so, this part is clear. Norm of a minus b is less than c. That part is obtained. Take it as equation number 1. So that part is obtained. Now we have to prove that minus c is less than a minus b. That is minus of this thing, norm y minus x is less than this quantity. So for that, we will take norm x. We do similarly. We add and subtract y. X minus y plus y. It can be x can be written as x minus y plus y. Now use triangle inequality in the normed space, that is norm x minus y plus norm y. Okay, now move this norm y onto the left hand side, that is norm x minus norm y should be less than or equal to norm x minus y. So norm now if we multiply this inequality throughout by minus, the inequality changes. So next step is we multiply by minus 1 on both sides. Okay, so the inequality changes. So the inequality becomes, so the inequality, if you multiply this by minus 1, the inequality changes to norm y minus norm x, since we have multiplied with minus 1. So less than or equal to becomes greater than or equal to minus of norm x minus y. We already know that norm x minus y and norm y minus x are similar, same. Okay, in that sense, because it induces a metric and metric has the same properties. So I write it on correct order. So minus of norm x minus y is less than or equal to norm y minus norm x. Okay, or minus of norm y minus x is less than or equal to norm y minus norm x. So this should be inequality number 2. From first inequality, norm y minus norm x is less than or equal to norm y minus x. From that, it is clear that a minus b is less than c. From the second inequality, minus of norm y minus x is less than or equal to norm y minus norm x. That is, minus c is less than a minus b. From these two parts, we use the definition of absolute value function. By the definition of absolute function, okay, we can say that we combine in these two inequality norm y minus x less than or equal to norm y minus norm x less than or equal to norm of y minus x. Okay, so c less than a minus b less than minus c less than a minus b less than c. From this, using the definition of absolute value function, you can clearly say that which can be written as modulus of a minus b less than c. So modulus of norm y minus norm x should be less than or equal to norm of y minus x. So this is how we obtain our preliminary result regarding the norm. Okay, so norm satisfies the same inequality which has been satisfied by the modulus. First result which we have obtained. Now moving on to the second result. So in this result, we will try to study the continuity of the norm function. So the result is the norm function, the norm is continuous. Okay, so it is defined as x, a vector onto a real number norm x. So this is continuous if it can be considered as a continuous mapping from the space onto R. So we have already known that this norm is a function from a vector space onto the set of all real numbers. We already know the essential condition for continuity of a function defined on a real space. So using that definition, if the function which is defined by us to define a norm or our norm function is continuous with regards to the basic continuity condition, then we can say that our norm is a continuous norm. So in general, our norm need not be a continuous norm. If it is considered as a continuous function, then our norm is said to be a continuous norm. So in general, a norm need not be a continuous one. That's what this says. Okay. Now moving on to some examples. Some examples regarding our normed spaces. So we have discussed about elementary properties of norm. We have discussed about the definition of norm. Now we are moving on to uh, some examples of the normed spaces. The first example is the Euclidean space R1, Euclidean space, which we have known R1, that is set of all n tuples x1 s2 etc xn such that xi belongs to R, and the unitary space Cn, which is set of all x1 s2 etc xn where each xi is a complex number. Okay, so what we are going to establish is that we will prove that these two things are actually normed spaces. So it should satisfy the condition which was defined by the norm. So this is what we are going to prove. Before getting on to much further details, we should be defining a norm. This is only a space. So here the norm is norm x should be equal to square root of theta 1 square plus theta 2 square plus etc. theta n square in the case of real numbers. And in the case of complex numbers, the norm is root of modulus of theta 1 square plus etc. modulus of theta n square. Okay, so here theta I are elements of R in the case of Rn and C in the case of complex numbers. So this is what our norm is. So we will be proving all the conditions be satisfied of the normed space being satisfied by the Euclidean space and the unitary space. The first condition is n1. So the first condition is norm x should be greater than or equal to 0. So here in the case of reals, norm x should be equal to, I will write in the simplified form, square root of summation j is equal to 1 to n theta j the whole square. We know that theta j the whole square is greater than 0. Then summation j is equal to 1 to n theta j the whole square is also greater than 0. So if we take the square root also, this square root should also be greater than or equal to 0 by the basic property of square root function. So clearly this should be greater than or equal to 0. It is not much to prove. But in the case of complex numbers, here instead of this theta j, we define as modulus of theta j square, which is clearly greater than or equal to 0. Then summation j is equal to 1 to n modulus of theta j the whole square, clearly greater than or equal to 0. If we take the square root also, the sum square root of this sum should also be greater than or equal to 0. So in general, norm x should be greater than or equal to 0. So moving on to the next property. Okay, so for next property, we have to establish norm x, the condition for norm x is equal to 0. So this is what n2. N2 is norm x is equal to 0 if and only if x is equal to 0. So this is what we have to prove. So clearly if x is equal to 0, so x is written as theta 1 etc. theta n, then theta I is equal to 0 for all I. Okay, then its square is 0, then sum of its square is 0, then square root of that is 0, then clearly norm x should also be equal to 0 when x is equal to 0, which is trivial. That is similar in the case of complex numbers as well. Now we have to prove the other way, that is norm x is equal to 0 implies x is equal to 0. The first x is equal to 0 implies norm x is equal to 0 is trivial. Norm x is equal to 0 implies square root of summation j is equal to 1 to n. I write just modulus of theta j the whole square so that it can be used for both real and complex numbers. In the real numbers and complex numbers, modulus of theta j square and theta j square are same. So this is equal to 0. This is equal to 0 implies summation j is equal to 1 to n modulus of theta j the whole square is equal to 0. Okay, so this is the sum of some positive quantities. Modulus of theta j square is always positive. So sum of positive quantities is 0, implies each of the quantities should be equal to 0. So which implies modulus of theta j square should be equal to 0 for all j, which further implies theta j is equal to 0 for all j, which implies x should be equal to 0. So the second condition is also